Okay, so we are resuming our recording on the lecture 2. So consider a fictitious company or computer company. We might ask the following questions. We want to know how actually the behavior of the customer in the computer company. So in that case, there are 4 questions you can ask. What are the probability that the consumer will actually buy a new computer? Okay, will actually buy it. So you basically have the action to buy, okay? And what's the probability that the consumer are planning to buy a new computer? So this one is just plan. So maybe you do some research and so on, but you don't really perform, okay, the buying action yet, okay? Yet, yeah, I'm using the word yet. And what's the probability that the consumers are planning to buy and actually will buy a new computer? So in that case, you're actually having a consideration over here, and so it's a intersection. And the last one, given that the consumer is planning to buy, what's the probability of a purchase? So this one is actually a bit different. Given that the consumer is planning to buy, so you know that you already have the knowledge, okay, that the consumer is planning to buy. It's actually different for the third cases where you want you want the events of consumers are planning to buy and actually will buy a new computer is happening together. That's the reason it becomes intersection. All right. Any one of it is actually not happening, then it's not considered as your count, okay, or it's not captured. However, for the fourth term, given that the consumer is planning to buy, so you are very sure, 100% sure that the consumer is planning to buy. You know that planning to buy event is happened. Okay, and what is the probability of a purchase? All right. So these 4 is actually 4 different perspectives for you to actually understand how the probability can give you different kind of information. So if we have an event A, there will be a complement to A. It's actually called A complement or B. All right. In here, we need to know something called marginal probabilities. All right. Because marginal probability is important as in when you need to sum only partial outcome of your events. Okay, when you know that there are actually a couple of events over there which is happening and affecting each other, but you just want to sum up one part of it. Later on, when we take into example, you have some better idea. But over here, it's actually trying to tell you that for you to calculate marginal probabilities, there are some concepts that you need to be very sure, all right? Including event A consists of 2 outcomes. It can have event A, it can have A1, A2. Like for example, if it's event weather, then A1 can be rain, A2 can be no rain, for example. Same goes to B1, B2, okay? So it's possible for you to have this kind of outcomes. And 2 events are mutually exclusive and disjoint if both events cannot occur together, and the set of events is collectively exhaustive if one of the events must occur. So these 2 we discuss further in the next few slides. We discuss about mutual exclusive first. So if A and B are disjoint, mutual exclusive events, then A or B equals to probability of A or B equals to probability A plus probability of B. So for example, let A is respondent lives in KL and B equals to respondent lives in Penang. Okay, and then you want to sum up the total respondents in that lives in Malaysia. So in that case, you have probability of A, which is like this, probability of B, which is like this, and then probability A or B equals to 0.193. In terms of a Venn diagram, okay, it's basically something you have your A and B disjoint or mutually exclusive. That's why you actually can sum up directly. How about if A and B are not mutually exclusive? So when you're calculating A or B, you need to minus the similar to this one. So you'll notice the probability is actually stronger only coupled with set theory. Let's see, circle, and then you actually have this one. Because whenever it's not mutually exclusive, so A and B can happen together. Okay, so in that case, A, B, so probability A plus probability B, when you are plussing A and B over here, you actually plus this particular middle region 2 times. That's the reason why you need to minus 1 round. Okay, so this one is quite, we actually discussed last week. But let's take into the example. It's actually one of the the slides is a bit chat, I think, last week, but this one actually fully explain about it. You have event that respondents sleep less than 6 hours per night. The events that respondents reports trouble sleep most or all of the time. So these two, you are actually having events that actually can overlap. You are not actually having a situation where A is talking about event that respondent sleeps less than 6 hours and B is event that respondent sleeps more than 6 hours. So when A and B can happen together. So in that case, you can actually plus up and then you get your answer, for example. Okay. But in that case, when these two are having a possibility, okay, for you to actually have it overlap. In that case, for you to calculate probability of A or B, you need all 3 information, which is probability of A to happen, probability of B to happen, and probability of A and B happen together. And for you to calculate this whole thing based on this equation. Okay, and you get the answer of this one. So this is why we need to know about mutual exclusive. How about exhaustive events? Exhaustive events is basically you want to, when you want to measure all the potential events that you actually have, okay, one of it must occur. At least one of it must occur. So in that case, for example, if you have 2 events A or B, when you are unioning it, you will actually get all the sample space of the outcome. So in that case, for example, if A is the event that respondents sleep less than 6 hours, and then B is the event that respondents sleep at least 6 hours per night, okay? A and B are exhaustive because when you have A and B union, you basically cover up less than 6 hours and at least 6 hours. You cover up the all potential sample space that you actually have. Okay, sleep less than 6 hours is 0 to 6. Okay, at least 6 hours is more than 6. Whenever you have this kind of situation, you basically cover all the possibilities, and then all the possibilities is falling into your sample space. Okay. So over here, we're actually showing some example over here. The first event, this is the second event. Exhaustive and mutually exclusive. Why? Because whenever you are union 1 and 2, the first event and the second event over here, you are getting 1, 2, 3, 4, 5, 6. All right, mutual exclusive. When this event is happening, this is okay. Sorry, when this is outcome. Okay, the outcome over based on the outcome they actually have. When this event is happening, this event will not. So in that case, it's mutually exclusive as well. How about this one? Mutual exclusive. When this outcome is 2 and this outcome is actually 6, based on the event that you actually have, 2 and 6. So mutual exclusive. All right, but not exhaustive. Why? Because this one is only having 2 and 6. But we know that the total potential outcome is actually 1, 2, 3, 4, 5, 6. Right? So mutual exclusive is correct, but this one is not exhaustive. This one is correct, this one is correct. How about this one? Odd and not 6. Odd is what? 1, 3, 5. Not 6. 1, 2, 3, 4, 5. Okay. Maybe this is not odd, this is even. All right. 2, 4, 6. That make more sense, okay? If it's odd, right, it's actually wrong. Okay, even. So, not mutual exclusive, but exhaustive. Why is it not mutual exclusive? Because the event outcome that actually have, you have 2 over here, you also 2 over here, you have 4 over here, you also 4 over here. You actually have it overlaps for your outcome that you actually have. Remember, when you actually your outcome have overlaps, your Venn diagram, you actually have overlaps like this. So in that cases, it's not mutually exclusive, but exhaustive. Why? When you are having these events, 2 event union having, you are unioning 2 events, then you have 1, 2, 3, 4, 5, 6. So you have 1, 2, 3, 4, 5, 6 for events from your sample space, cover up all the samples, potential samples. So that's the reason why it is considered as exhaustive. Okay. How about for a coin toss? So please think about it, yeah? Coin toss example is much more straightforward. Okay. Okay, after we talk about mutual exclusive and collective exhaustive events, right now, one of the most important concept in probability is independence. So 2 events are independent if the occurrence of one in no way affects the probability of the other. So you always need to check the questions or the explanation on the environment. How is it tells you that whether it's independent or not for you to decide. Okay, but once you have decided independent or non-independent, your formula will eventually different. Okay. Because why? When it's actually independent, right? Even though you know that A is happening, but A doesn't affect B. That's the reason why when it's independent between A and B, your probability of B given A over here, your probability of B given A over here can change to probability of B here. Because knowing that event A to happen doesn't tell you more about the probability for B to happen, because the probability of event A and B are independent. So the example, yeah. So over here, this example is actually trying to tell this one. A1, A2, B1, B2, right? You have event A and B. Then you can actually have plan to purchase, actually purchase. If you still recall the example that we have just now, then you can have A1, A2 is yes and no, B1, B2 is actually yes and no, and actually can tabulate the outcome for 1,000 customers. So this somehow your data. Okay. And if A equals to plan to purchase and B is equals to actually purchase. So in that case, for you to calculate P, plan to buy, over here, this is actually the process for you to calculate a marginal probabilities. Why? Because you only consider probability of plan to buy, regardless of whether the event B, which is did they actually buy or not. So in that cases, you need to consider both potential outcome of buying or not buying, because both of them having the potential probability of plan. So you actually plan to purchase is this one. So you are calculating this whole part, but disregarding this whole part. All right. Maybe I draw in the better manner. Disregarding this whole part. Okay. So in that case, this is considered marginal probability for probability of plan to buy. You can actually calculate another marginal probabilities for no plan to buy. You can actually calculate a marginal probability of actually purchase, okay, based on the column this time. Or you want to calculate marginal probability of actually not purchase based on the column. All right. So this is a concept or what we call as marginal probabilities over here. You only sum up the partial probability based on the events that you have. Okay. So in that case, from here, probability of A1 and B1 plus probability of A1 and B2. Because why we are actually considering A1? Because A1 resembles plan to buy. This is actually the A1. Okay. And you are actually not calculating about A2. But you take every single potential outcome of A1. So A1 and B1 happen together, you sum it up. A1 and B2 happening together, you sum it out as well. So that's why you are getting this one from here and from here. And you sum it out, you get a probability of 0.25 or 25%. So if you are having difficulties on doing tutorial 1 question 6, I mean with the table, if I recall correctly, then this one will help you a bit. Okay. Another example, there are 40 female students in the class of 100. Okay, 10 of them are from some foreign countries. 20 male students are also from foreign students. And then you're actually having A and B like this. Student from foreign country, and B is actually a female student. So over here, how you actually can draw it. Okay, we take a look. We have 40 students in a class of 100. So we are actually getting this. We actually supposed to start from getting female 30 first, right? And then total is 100, but we don't have extra enough information, so we leave it there first. 10 of them are from some foreign countries. Sorry, 40. Yeah, this one is 40. But you know that among these 40 females, there are 10 is actually from foreign countries. So this one is 10. Okay. Maybe I try to draw it again. I just put here, female is 40, but you know that there in here this one is actually 10. So 40 minus 10, all right. Maybe I put the F outside. Female. All right. 20 male students are also foreign students. So for you, okay, to know that, for you to, this one is foreign students here. This one is foreign students. And then you know that there are 20 of them are actually males. Okay, supposedly when you're actually having female over here, you're actually having female over here. The rest of the thing, okay, maybe I put a big square over here. The rest of the thing is supposed to be male, okay? But right now, your male information actually having one extra information from foreign students as well. Male students are also foreign students happening together, and this one is actually 20. That's the reason why this one is 20 over here. And remember, you have one final information. The student is actually a class of 100. And after all these 30, 10, and 20 inside your blocks, so you know that 100 minus 60 inside over here is actually 40. And this 40 is actually, maybe I put in female inside. What else is confusing? And then foreign student. I put just FS over here. And this one is actually male and also non-foreign. And this is how you are getting this. All right. Okay. So this is how you are getting this one based on here, right? And how about complement? complement, we actually understand the concept of complement, but when you're drawing based on Venn diagram, okay, you can see the example here, yeah. So this one is actually, if you're just considering the female and the rest of this one is actually your complement, which looks like this. And if you're just considering foreign students, this one, then the rest of it is actually your complement, which is looks like this. All right. So all these that we actually discussed just now are all revisits. We are actually moving into conditional probability in a more detail because why? Conditional probability is fundamentals for Bayes' theorem. Okay, so the conditional probability of A given B, yeah, A given B is the joint probability of A and B, which is this one. So sometimes probability of A and B can be written like this, okay? Or it's actually similar to probability of A intersect B. It's actually the same, yeah? Divided by the marginal probability of B, okay? So you'll notice that marginal probability of B, basically, you're only having one events inside, okay? But when you're actually putting in over here, probability of B, you're actually covering all the potential events that is when B is actually happening, all right? Why is it B? It's because when you know B is happening, you are actually shifting your sample space from a large set to a smaller set, okay? When this smaller set is actually based on the probability events of B. That's the reason why the B becomes your denominator this time. Remember, previously your sample space is actually in your denominator, but this time it becomes your probability of B. Because you know B is happening, so your sample space is actually reducing. Okay, so it's like when you know that this whole thing is your sample space, but right now you only consider a small B events inside. Okay, if it's this one is your sample space. So thus, if A and B are statistically independent, okay, when it's independent, so you actually can expand this way. Probability of A given B equals to probability of A intersect B divided by B. But when you're actually having these intersections, okay, you can actually expand it to become probability of A times probability of B. Why? If you still recall, I think it's a few slides back. Let me see. Independence of this one. Okay, probability of A and B. Okay, so it's again same with probability of A, B, probability of A intersect B, the same one. So we have discussed just now, so we know that probability of A intersect B equals to probability of A times probability of B. Okay. So once you have substituted over here, probability of B and B you can cancel off. So in that case, probability of A given B equals to probability of A. All right. Information from B doesn't really give you any contribution on knowing the probability of A because of the statistical independence. When they are statistically dependent, then in that case it's actually different. All right. So that's the reason why for you to identify whether it's independent or not is very important. And so this one is actually just another way of rewriting it. You have joint probability of X and Y, and then marginal probability of X, and you basically getting this one. Okay. Okay. So this one is actually it's still very fresh, right? This one, and then for you to calculate the probability for you, probably you purchase a computer, given that you actually plan to purchase. So given that you plan to purchase, it's actually some evidence, okay, or something that you already know is happening. So it's actually supposed to be behind, okay? Given that you plan to purchase, it's actually over here. And the probability that you actually purchase a computer, so you want actually in the other day, you want to calculate this one. That's why it's actually in front over here. And if you're trying to look into here, it actually is probability of B1 given A1 because it's this one and this one. All right, both yes. And then when you expand it, it will become probability of B1 and A1 happening together, which is this one. 200 divide by 250, and you get, all right? So you notice that if we just calculate probability of B1, okay, it's actually like this, right? It's actually 300 or 30%. But when you know that it's actually planning to purchase, it's actually changing from this one to this. So this information actually gives you more idea on the outcome itself. There are some property that we actually need to know about the conditional probability. So this one is we are already talking about it just now. So it's actually this one. So it's actually this one. So it's the same. And how about probability 2? The multiplication rule for conditional probabilities. So in an experiment involving two independent events, A and B, the probability of A and B occur can be found in the two following ways. So when you're actually having probability of A intersect B, when you want to expand the potential outcome, it can looks like this, or it also can looks like this. Okay. Why? Why? Because remember, this one, yeah, so it's actually coming from here. So if you're actually getting this one, all right, if you're actually getting this one, then in that case, you are, okay, this one's AB, right? So this one is over here, and then B is over here. Okay, so based on this formula, yeah, this one is definitely correct. How about I write another one? Probability of B given A equals to probability of B intersect A, probability of A. I mean, basically similar, right? I'm just changing the place of A and B. All right. So this one is actually reflecting this. All right. And this one is reflecting this. And this one, okay, this one is actually reflecting this. You notice that probability of B given A is actually same with probability of A intersect B. Sorry, B intersect A is actually same with probability of A intersect B. I mean, when you're doing an intersection, no matter which one is in front or which one is behind, it's still giving you the same thing. Just two events happening together. So that's why you can actually write your intersection in both ways. All right, the multiplication rule. And because of this, okay, we are actually able to write about Bayes' theorem. All right, okay. Bayes' theorem is actually something that you try to know the posterior probability, or you want to know in more detail when you actually given certain kind of evidence. Okay, are you able to to calculate a more somehow accurate probability once certain kind of evidence is actually given to you? All right. For example, yeah, idea. You have someone is shooting at the target. If it's windy, you have a 40% chance. If it's no wind, his chance is 70. If there is a 12% chance of getting windy, what's his chance of hitting the target? All right. And if he hits the target, what is the chance of being windy? You actually notice that there are two main things. One is windy, and the one is whether he hits the target or not. And Bayes' theorem will be actually able to calculate it exactly when you're actually having these kinds of information. Okay, you have some probability in terms of whether being windy or not, or whether he's hitting chance based on different kind of conditions. And these conditions is actually helping you to calculate your final outcome in terms of the probability that you are intended to get in. Okay. So Bayes' theorem is basically this one. Okay, of course, it's introduced by Reverend Thomas Bayes. And Bayes' theorem for probability of events A and B is actually expanded from here. If you notice that this one, okay, is actually probability of A intersect B equals to probability of A given B equals to probability of A intersect B, probability of B, right? And this probability of A intersect B can be changed to probability of B times probability of A times B. Because the multiplication rule that we discussed just now, it can have two different formats, right? But if you are following the original format, then basically your equation have no meaning at all. So that's why you are using another one right now, which is the bottom one, probability of BA PA divided by probability of B. And since you know that you want to calculate probability of B, okay, probability of B is actually marginal probability of B to happen, right? So in that case, it will actually become probability of B happens. Okay. Okay, probability of B happens given A times probability of A. All right. This one can be A1, this one can be A1, this one can be A1, this one also can be A1. Okay, because your A, A1, A2, A3, and so on. So you can have many different A's. Okay, but of course, most of the example that we have discussed previously is A are mostly on only two, yes or no, for example. But it can have more than one A. Okay, but if you're just considering two outcomes, it will look plus probability of B A complement and then probability of A complement. Okay, you are considering this one should be B is happening, all right, but A is happening as well. And this whole thing is considering B is happening. Okay, remember your marginal probability is always calculating B is happening, for example, over here. And this time you are considering A is complement. A is not happening this time. So this one is B is happening, A is happening. But this one is B is happening, A is not happening. Because why? You want to capture every single possibility under marginal probabilities of B to happen. Okay. But this one, you are only capturing the A that you are interested. That's why you can have just A itself. Okay. Or if you are interested in A complement, then you can put the A complement. So in general, this one is just the one term among of the 1, 2, 3 terms that you actually can have based on this equation. Okay. But in general, maybe it's just two terms that you actually have. All right. We try to see some practical questions. But before that, there are still some theories to follow. Think of Bayes' theorem as a probability in reverse. Okay, you can actually update your probabilities in light of the new information, right? You're actually trying to calculate, okay, new sets of probability based on the information that is given you extra. Okay, so suppose you have a product, example over here, suppose you have a product with a known probability of success, we will have success 0.4 and then failure 0.6. So we also know the customer group will actually write either a favorable or unfavorable report on the product, which is favorable or unfavorable. So this favorable product is actually, for you to write favorable, is actually 0.8. So in that case, if you still recall your collective exhaustive event, because one of the didn't turn on. Oh, yeah. One example is actually, sorry, Bayes' theorem is actually based on mutual exclusive and collective exhaustive. Okay. So in case, if you still recall what you have learned previously just now, the concept, then your probability of F complement given S is actually 0.2. Okay, and then this one probability of F complement given S complement is actually 0.7 because you are doing one minus over here and also one minus over here. Then you have basically have 4 values over here. You have 1, 2, 3, 4 values over here. So we want to find the probability that the product will be successful given a favorable report. Okay, so you actually want to calculate it. So notice that originally you actually have PS, probability of success. Right now, you want to calculate probability of success again, but given that you are actually given a favorable report. Okay, so in that case, if you notice that your Bayes theorem right now, I mean your example over here right now, you only have success and failure. So you only have favorable or unfavorable report. Yes and no. They are actually binary outcome. So in that case, for you to apply Bayes theorem, it looks like this. Okay, it's actually same with your formula, which I actually having over here. Okay, this formula and this one is actually same because in over here we are only considering S and S complements. Of course, if you want to make it more similar to this formula, you can actually put in this one is S1, this one is S1, this one is S1, this is S1, S1, this one is S2, this one is S2. Okay, that anyway, if you are right in this sense, then it's closer to this in terms of numbering. They actually have. Okay, anyway, this one, I mean, this rewriting is still valid because we only have 2 particular outcomes. So in that case, for you to calculate this, you need to have all these information, 1, 2, 3, 4, 5, 6. Do you have probability of F given S? Yes. Given from the question. Do you have your probability of S? Yes, over here. Do you have probability of Fs? Similar and similar. So you do basically just need to copy it down. So 0.8, 0.4, this one is 0.8, 0.4. How about the complement of S? Probability of F given S complement. Oh, probability of F given S complement, 0.3. Probability of S complement, 0.6. So 0.3, 0.6, and when you sum it up, calculate, and you get 64%. And you will notice that it's actually changing from 0.4 for probability of success to, I mean, your probability of still success, but given that your favorable report is actually increasing the chances for you to get your success. So given the favorable report, the chances of success is increasing. Okay. And basically, this is what we call as updating the probability because of you are actually getting a favorable report. Okay. So if you see the difference, highlight again, you actually get from PS, probability of success, changing to probability of success, more information. Okay. So over here, Bayes' theorem deals with sequential events whereby new additional information is obtained. Okay. New additional information is obtained of a subsequent event, and that new information is used to revise the probability of the initial event. So just now we're actually having probability of S as your initial event, which is, in other words, prior probability. An initial probability value that originally obtained before any additional information is obtained. Okay, but later on, when we actually know that we are getting a favorable report, you're able to actually calculate probability of favorable report, okay, which becomes posterior probability. Means that it's a probability value that has been revised, okay, revised And originally or initially it's actually different. Yeah, this one is revised by using additional information, and this additional information is actually your favorable report that's later obtained. So this is how you actually can differentiate these two. So another example here, the Gallup for a survey about credit card usage. So use a subjective probability to estimate the following. So what's the probability that a selected subject is a male? Okay. And after selecting a subject, it's later learned that this person was smoking a cigar during the interview. So what is the probability that the selected subject is a male? Which one is preceding to result in the probability? Which one is posterior probability? So when you are checking in these questions, okay, of course, we don't have any values over here. It's a theory-wise question. What's the probability that the selected subject is a male? You're basically trying to calculate the probability of male over here. Okay, after saying the subject is later learned that this person, you see the extra information, was smoking a cigar during the interview. What's the probability that the subject is actually a male? The probability that you're actually measuring is still male. But right now, you're actually getting an extra information about smoking a cigar. That's why it will become probability of M given C. From probability of N, it becomes M given C. So in that case, which one is actually prior and which one is actually posterior? Of course, prior is this one because it's the initial probability, while posterior is actually this one. Of course, these are the explanations. 0.5 and 0.85 is, but all this is actually coming from statistical analysis, of course, of all this kind of data. So, and with probability kind of conceptual questions, it will always be given to you. Okay, for to solve the question. So these two are just explanation, yeah. Yeah. So in orange country, another example, 51% of the adults are males. So one adult is randomly selected for a survey involving credit card usage. So find the prior probability that the selected person is actually a male. Prior probability, this one. All right. This one, you don't have anything at all. You just know that 51% of the adult in the orange country is males, are males. So in that case, 0.51 or 51% is your answer. How about it's later learned that the selected survey subject was smoking a cigar, and we have extra information from the study where 9.5% of the males smoke cigar, whereas 1.7% of the female smoke cigars. This one, you're actually giving you the information of probability of smoking cigars, given that it's male, and this one is actually smoking cigars, given that there is not male or it's actually a female, your choice. You can actually put in CF as well. It's the same. Okay, but then you need to be very careful because you know that male and female is actually mutual exclusive and collective exhaustive. So these are the two outcomes there, two events that you're actually can having. Okay, so that's why it's actually this female is actually equivalent to the complement of M. Right? So use this additional information to find probability the selected subject is a male. This additional information will actually help you to calculate probability of M given C for your question C. Okay. So same. When you are actually probability of M, then you will also be able to get probability of M complement because 1 minus probability of M equals to probability of M complement, which is 0.49. For this one, it's 0.095 because 9.5% of the males smoke cigar. So you're actually calculating the probability of smoking cigar, given that it's actually a male. Okay. Again, you're actually able to calculate C complement M as well. Same goes to this one, probability of C complement given M complement. Then, initially, we knew that the subject is smoke a cigar, so therefore it's a 0.51 probability the subject is a male. However, After learning the smoke a cigar, you revise the probability of 0.853, which is coming from here. 8533, sorry. This makes sense because the likelihood, okay, here, over here, the word likelihood basically tells this one and this, all right? The likelihood of males increase dramatically with the additional information that the subject smokes cigars, because so many more males smoke cigars than females. See, when you're comparing these two values, okay, it's actually like 5 to 6 fold, okay, 5 to 6 times difference. That's the reason why when you're actually getting extra information about their gender, it gives you a boost in terms of a probability distribution. And in terms of calculations, you need to know about probability of MC equals to probability of M times probability of C given M. Okay. Basically, when you're actually writing this one, you can actually have some trick. Okay. For example, here probability of M given C equals to, reverse it first, probability of C given M. Okay. And then you also write times the probability of the evidence of the one that you have reversed. So it's actually M itself. So probability of C given M times probability of M. And this term and this term is always the same. And the last term over here is always the complement for the evidence that you actually have. I mean the evidence in terms of over here, but it's actually the one that you want to measure. So that's why from here, from this formula that you actually have been derived, you actually have 0.51 over here, which from here, 0.095, which is probability of C given M, which is from here. These two are the same. Probability of M complement, 0.49, which is here. Probability of C times the C given M complement, which is this one, 0.017. And you will get 0.533. So this is how you see from 0.51 probability, if actually increase to 0.85, a very big increase, okay? Another example of Bayes' theorem. The doctor knows that meningitis M over here, we have already written this one over here, causes stiff neck, okay, 50% of the time. So you notice that this one is actually, okay, probability of the meningitis cause stiff neck. So probability of stiff neck given meningitis, okay, because you are talking about meningitis causes stiff neck, but it's only 50%. So when you are rewriting this part, it's actually probability of stiff neck to happen given that meningitis. Okay, so that's why it's 50%, and it's actually putting over here. Prior probability that any patient having meningitis is 1 over 50,000. This one, you don't really apply a full Bayes theorem, but yes, it's still Bayes theorem. It's just that this one is still your marginal probabilities over here. But once you are actually getting the Bayes theorem done over here, you need to know the probability of meningitis as well. Prior probability that any patient having meningitis is this one. So you have over here, which is like this. And the last one, probability of S, probability of any patient having stiff neck. So this one is actually here. So that's why you are getting 1 over 20. And once you solve this one, you get 0.0002 or around 0.02%. Okay. So it's not only one way like, it's not only just one way like you always need to expand in the so-called complicated manner. It depends on the questions, whether it gives you the information that you need to solve the Bayes theorem or in this way, right? The last one on the another example on 8. So suppose the probability for anyone is 0.01 and also 0.08. Typo here, 0.001. Okay, and no x is 0.999. Okay, and consider an 8 tax. Result is plus or minus. Okay, so you of course, this A test you go and conduct it, and at the end of the day it gives you back all the probability that you actually have. Remember, all this is actually likelihood for it's to happen. Okay, given the A to happen, the likelihood for you to get positive is 0.98 and etc. Okay, so this time is actually we do the complement directly this round. Okay, probability for you to have 8s given a positive result is probability of 8s. You see here, originally is probability of 8s, prior probability over here, and then you want to calculate the probability of 8s given positive. Okay, so right now you are considering a posterior probability by knowing when you know that that particular patient is getting a positive test. So again, once you are getting these probability values, probability calculations that you need to apply on the equation that you actually have, just reverse it first, and then you write the somehow the evidence now to be a probability. So you become probability of positive given 8 times probability of 8. Okay, and then divide by the whole thing over here, the marginal probability of 8 happening. Okay, the marginal probability of a positive, because this one is actually your evidence. So this whole thing is a marginal probability of positive. So notice that the probability you're calculating just positive and positive, negative is not inside. But regardless of the probability of 8s or no 8s, you are still summing it up. Okay, so in that case, you actually can get all this from the table, from the information that we actually capture over here, and you get 0.032. And from your viewpoint, these probability values basically trying to tell you that, okay, even though I'm tested positive, there may be still have chances that I'm not getting the 8s. So the percentage is, for you to get 8, if you are tested positive, is 3.2%. But your doctor's viewpoint is actually 3.2% of the people like this, you have 8s. So from your point of view, it's actually your degree of belief, because you are your own as a whole. Okay, you're one person as a whole. But from the doctor's viewpoint, they have many patients, so they will actually feel that, okay, among 100 patients that tested positive, 3.2 of the people will actually have the 8 self. Okay, so the doctor's viewpoint and your own viewpoint is actually a bit different. Okay, so that's all at the moment for the base theorem. So during the lectures going on, which is from 9 to 11. So we are that's all for today's pre-recorded lecture. Thank you.